9.1 Systems of Linear Equations. Well, previously we talked about solving a system of two linear equations and two unknowns, and we were able to determine whether it was a conditional system where there was one solution, an inconsistent system where there were no solutions, or a consistent system where there was an infinite number of solutions because both equations represented the same line. Now we're going to expand this out and we're going to look at a system with three linear equations and three unknowns. Now the method is very similar, it's just a little extended. So what we're going to do is we'll start with the three equations and we want to eliminate a variable. And then we want to eliminate another variable, so we get down to one equation with one unknown. So we're going to start out with three equations and three unknowns. We're going to eliminate a variable and get down to two equations with two unknowns. And then we're going to eliminate a variable and get down to one equation with one unknown. Solve for that unknown or that variable. Then plug it back into our system of two equations, or an equation which had two unknowns, so that we can find the second variable, and then plug both of those into one of our equations that had the three unknowns to get the third variable. So it's just an extension of what we already did. Now we can use substitution or we can use elimination for this. It depends on what we feel is going to work best. Many times I use elimination because I feel it's more consistent, so that's probably what I'm going to end up using. But we'll see. So let's look at an example. I have 3x plus 4y minus 2z is equal to 14. 2x plus y plus 2z is equal to negative 9. And x minus y plus z is equal to negative 9. So I have three equations and three unknowns. And what am I going to do? Well, remember my options are, I can use substitution, so I could solve this equation for one of the variables. Like I could solve this equation for x. And if I were to do that, I would get x is equal to y minus z minus 9. And if I did that, then I could plug y minus z minus 9 in place of x in both of these equations, and then I would have two equations that are in terms of y and z. I could then solve one of those equations for y in terms of z, and plug that into this equation for y, and have it as one equation in terms of z. Solve for z, and then plug that into the equation with two variables to solve for y, plug that into the equation with three variables to solve for x, and I could get all of my values. So that's one method I could do. The other method is I can choose any two of these equations and eliminate. Use them to eliminate a variable. I can then choose any other combination of two equations and eliminate the same variable, taking me down to two new equations with two of the same variables. Then I can use those two to eliminate an additional variable and get down to equation one variable and then work my way back up. The biggest thing to pay attention to in this is you have to eliminate the same variable both times. I look at this and I go, if I'm going to deal with elimination, let me get this out of the way just because I'm not going to use substitution. But if I'm going to deal with elimination, using those first two equations seems pretty easy. I've got negative 2z, I've got positive 2z. So if I add them, z is going to disappear. Looking at the second two equations, I've got plus y and minus y. If I add those two together, then y is going to disappear. The problem, though, is that would leave me with, this one would leave me with an equation in terms of x and y. This combination would leave me with an equation in terms of x and z. So I'd be down to two equations and three unknowns, and that's a bad thing. Because if I have three unknowns and two equations, I cannot solve for the values. All I can do is write them in terms of one of the variables. So we want to be careful about that. Whereas if I can combine two of them and get rid of a variable and get it down to two, then combine another two and get it together, and to combine and get rid of that variable, then now I can get down to two equations, two unknowns. So let's stop talking about it and actually do it. So I see here that if I add these two together, I can get rid of z. So I'm just going to write them over here. 3x plus 4y minus 2z is equal to 14, and 2x plus y plus 2z is equal to negative 9. If I add those two equations together, my z's are going to cancel out. 3x plus 2x is 5x. 4y plus 1y is 5y. Negative 2z plus 2z cancels out, gives me 0 z's. 14 plus negative 9 gives me 5. Okay, so I have one equation with two unknowns. Now, I can choose any other combination of two equations. So I could choose this first one and the last one, or I can choose the second one and the last one. I can't reuse the first two again because then I'm just going to end up with the same equation. So I think I'm going to choose to use the first and the third this time. So I'm going to go through it again, and this time I'm going to do it over here, just to keep it separate from that. So I have negative 2z here, so I'm going to multiply this equation by 2, because then I can turn this into 2z so I can cancel it out. So I'm going to take 3x plus 4y minus 2z is equal to 14, and I'm going to multiply that through by 2, so I have 2x minus 2y plus 2z is equal to negative 18. So I've got minus 2z, I've got plus 2z, so I'm just going to add those two together. 3x plus 2x gives me 5x. 4y plus negative 2y gives me 2y. Negative 2z plus 2z gives me 0z. And 14 plus negative 14 gives me negative 4. So now I have two equations and two unknowns, x and y. I've got 5x plus 2y is equal to negative 4, and I've got 5x plus 5y is equal to 5. So now, if I've got two equations and two unknowns, we can do what we've done before. So, just going to go over here and say, okay, I've got 5x plus 5y equal to 5. Well, let's put this one below it. 5x plus 2y is equal to negative 4. And I see 5x and 5x, so if I subtract that second equation from the first one, it'll cancel out my x's. 5x minus 5x is 0x. 5y minus 2y is 3y. 5 minus negative 4 is 9. 3y is equal to 9, divide both sides by 3, and I get y is equal to 3. So now I have one of my variables. I can now take that and substitute that into either one of my two variable equations. It doesn't matter which one, because I just need to plug this in here and find out what x is. So I'm going to choose the top one. So I'm going to go 5x plus 5 times 3 is equal to 5. So 5x plus 15 is equal to 5. Subtract 15 from both sides, so 5x is equal to negative 10. Divide both sides by 5, x is equal to negative 2. Negative 10 divided by 5 is negative 2. So now I have y is equal to 3 and x is equal to negative 2. Well, let's go, now we have two of the variables, we need the third one. Let's go back to one of our original equations. Being lazy as I am, x minus y plus z equal to negative 9 looks like the easiest one to deal with, right? I don't have to deal with all these multiplications, I'm just plugging the numbers in to find out what z is. So I'm going to go x is negative 2 minus y, which is 3, plus z is equal to negative 9. Negative 2 minus 3 is negative 5, plus z is equal to negative 9. I add 5 to both sides, and z is equal to negative 4. So now I have the solution, negative 2, 3, negative 4, x, y, and z. That's an ordered triple, right? An ordered triplet, x, y, and z, negative 2, 3, and negative 4. And now is where I get to go through and verify that it actually works in all of these. So I'm going to switch to red for that. So we're going to take 3 times negative 2 plus 4 times 3 minus 2 times negative 4 is equal to 14. That's negative 6 plus 12 plus 8 is equal to 14. Negative 6 plus 12 gives you positive 6. 6 plus 8 is 14. 14 equal to 14. That one worked. Let's take the second equation. 2 times negative 2 plus 3 plus 2 times negative 4 is equal to negative 9. 2 times negative 2 is 4, plus 3. 2 times negative 4 is negative 8, minus 8 is equal to negative 9. 4 plus 3 is 7. Minus 8 gives me negative 1. So I've got a problem. Did I make it? Oh, here we go. This is why we do it, right? 2 times negative 2 is negative 4, not positive 4. So negative 4 plus 3 is negative 1, minus 8 is negative 9. So negative 9 is equal to negative 9, and we're good. Okay, let's verify it in the last one. It should work in the last one because that's where we got our final value from, but we still want to make sure, just to make sure we didn't make a mistake somewhere. So negative 2 minus 3 minus 4 is equal to negative 9. Negative 2 minus 3 is negative 5. Minus 4 is negative 9. Negative 9 equal to negative 9. And yes, it did work for all three equations. So negative 2, 3, negative 4 is a solution to our system of 3 linear equations. So remember, it's the same process that we did with 2 equations and 2 unknowns. We're just taking it further. So the key thing is, take 2 of them and use it to eliminate a variable. Take another set of 2 of them and use it to eliminate the same variable. Once you do that, you get down to a system of 2 equations and 2 unknowns. Use them to eliminate a variable, you get down to 1 equation and 1 unknown. And this process works no matter how many variables and equations you have. So if you have a system of 10 equations with 10 variables, you can do it by taking sets of 2 equations and eliminating the same variable to get down to 9 equations and 9 unknowns. And then using sets of 2 equations to get it down to 8 equations and 8 unknowns. The same thing to get it to 7 equations and 7 unknowns, and then 6 equations and 6 unknowns, 5, etc., until you get down to 1 equation and 1 unknown, and then you build it back up finding each of the individual values as you add on a variable to the equations. Okay, so let's get this out of the way. And there's one more thing I want to show you with this. Now, if you remember when we were dealing with two equations and two unknowns, and we came up with a consistent system, we actually ended up solving the equation. Remember, consistent system is where you have an infinite number of equations, or I should say infinite number of solutions, because the two equations are the same. So you came up with the solution as a variable and the other variable written in terms of that variable. Well, using a similar method, if we have a system of n variables, or we have n variables in n minus 1 equations. So if we have a system of 8 variables, but only 7 equations, then we can solve to the point where we can give the solution in terms of one of the variables, but we cannot solve to find out the actual solution itself. So we have to have it in terms of one of the variables. Now, if that's the case, we can choose any of those variables. So what we're going to do is we're going to look at a system with 3 variables, but only 2 equations, and we're going to solve that system in terms of one of the variables. And since we're going to have 3 variables, x, y, and z, it's really up to us to determine whether we want to serve it all, and whether we want to solve it all in terms of x, or we want to solve it all in terms of y, or we want to solve it all in terms of z. Sometimes we're told to solve it in terms of a certain variable. Other times it's just a matter of which is the easiest, and then do it. So let me grab my example. (3x plus y minus 2z is equal to -7. 5x plus 2y plus z is equal to -6. Now, as you can see, we have 3 variables and only 2 equations. So if that's the case, how do we solve it? Well, we can still use substitution or elimination to get rid of a variable. Once we get rid of one of the variables, then we can write the other variable in terms of a variable. So let's say we get rid of z, we can then take whatever's left over with x and y and write x in terms of y. X equal to something, y something. Or we can solve y in terms of x and get y equal to something x plus something. So we can then use that to go and determine what z is in terms of x, or what z is in terms of y, and come up with three things: x, a function of x, and a different function of x for x, y, and z. Or we can come out with a function of y, and a different function of y. Or we can come out with a function of z, a different function of z, z. So rather than me stating that over and over again, let's take a look at it and see how we can do it. So I'm looking at this, I see 3x, 5x, I see y, 2y, I see -2z, and I see positive z, and I'm looking at it going, well, what's the easiest thing for me to eliminate? First of all, I tend not to do this as substitution. Now you could, it would be very easy to solve this z in terms of x and y, and then I could plug that into here and have this in terms of x and y, and then solve for one of those variables, and then I'd have x in terms of y, or y in terms of x, whichever happens to go for, and then I could plug that in, and I could get the other one. But I'm going to do it by elimination just because I kind of see that as easier. So to do that, I think what I'm going to do is I'm going to multiply the top one by 2. So I'm going to end up getting rid of y. Why? Because I chose to. Actually, the reason I'm going to do that is because if I multiply this one by 2, then I can put my new equation underneath this one and they're right next to each other. Whereas if I multiply this bottom one by 2 so I could cancel it, then I'd have one equation up here and the other one up there, and I'd rather have them right next to each other. So multiplied by 2, I get 6x plus 2y minus 4z is equal to negative 14. See, now I have these two right next to each other, so I'm going to subtract the bottom one from the top one. So this 5x minus plus 2y plus z equals negative 6 minus 6x plus 2y minus 4z equal to negative 14. So I'm going to subtract. So 5x minus 6x gives you negative x. 2y minus 2y gives you 0y. Z minus negative 4z gives you z plus 4z, or 5z. Negative 6 minus negative 14 is negative 6 plus 14, which gives you 8. So now I have, don't forget your plus in here, right? Now I have negative x plus 5z is equal to 8. Now, I see in this that solving for x should be really easy, which means I can then write x in terms of z. So that's what I'm going to do. So I can say negative x is equal to negative 5z plus 8. Divide both sides by negative 1. X is equal to 5z minus 8. So I now have x in terms of z. Well, that's good. Well, if I have x in terms of z, I can now use this and get one of these other equations where I have y and z. So I'm going to take this bottom one just because. So I'm going to substitute in for x with 5z minus 8. So 5 times 5z minus 8 plus 2y plus z is equal to negative 6. 5 times 5z is 25z. 5 times negative 8 is negative 40. Plus 2y plus z is equal to negative 6. Combine like terms, 25z plus z is 26z. Plus 2y. And if I add 40 to both sides, I get 34 is equal to 34. So now I'm going to solve for y in terms of z. Why am I going to do that? Well, I have x in terms of z. So if I get y in terms of z, then I can write the whole set of solutions in terms of z. So I'm going to subtract 26z from both sides, so I get 2y is equal to negative 26z plus 34. I can divide by 2, y is equal to negative 13z plus 17. So I now have x in terms of z, I have y in terms of z, and we should know, or it should be obvious, that z is equal to z. So I have z in terms of z. So my solution, or one of my solutions to this system of 2 linear equations and 3 unknowns is x, 5z minus 8, y, negative 13z plus 17, and z. So I just solved this system of 2 equations and 3 unknowns in terms of z. Give me a z, and I can give you the 3 values. So if z is equal to 1, then I have 1 for z. Negative 13 plus 17 is 4. 5 minus 8 is negative 3. So that's a solution to this system. And you can plug it in and see if that works. Negative 9 plus 4 is negative 5. Minus 2 is negative 7. Negative 15 plus 8 is negative 7. Plus 1 is negative 6. So that worked. And I can plug a different value in for z and get it. So that this set of expressions in terms of z gives me all of the solutions to these two equations in 3 variables, or 3 unknowns. So that's not bad. That's pretty good, and that allows us to do a lot with it. So, I do want to cover one more little thing on this. Okay, so if you got a system of equations to model data, and we have 3 points on a graph, we can find the equation of a parabola y equals ax squared plus bx plus c by solving a system of 3 equations with 3 variables. So let's find an equation in terms of y equals ax squared plus bx plus c that passes through the points negative 5, 7, negative 1, negative 2, and 3, 5. So the question is, how are we going to do that? Well, we can do that by taking any of these points, well, I should say, by taking these points and substituting in to this equation to then find A, B, and C. So let's see what happens if we put negative 5, 7 into this equation. So that means 7 equal to A times negative 5 squared plus B times negative 5 plus C. Okay, so that's one equation. I can now plug this one in and get negative 2 is equal to A times negative 1 squared plus B times negative 1 plus C. And I can plug the third point in. 5 is equal to A times 3 squared plus B times 3 plus C. So what have I done? I've just taken this generic quadratic equation and I've plugged the 3 points in for x and y to turn it into what are 3 linear equations in terms of 3 variables. So if I rewrite this top one here, we see that I have, I'm just going to write it in a slightly different order too. Negative 5 squared is 25, so I have 25a minus 5b plus c is equal to 7. Here I have negative 1 squared is 1, so a minus b plus c is equal to negative 2. And 3 squared is 9, so 9a plus 3b plus c is equal to 5. So I've just come up with 3 linear equations, all in the form ax plus by plus c. Right, so 3 different variables, so constant times a, constant times b, constant times c is equal to a constant. So 3 linear equations with 3 unknowns. To give us some space, I'm going to get rid of these over here. And I'm going to start solving. Well, it should be relatively obvious that I've got C, C, and C, so I can take any of these and just start subtracting to cancel, and I'm going to be able to cancel out C's pretty easily. So 25A minus 5B plus C is equal to 7, and A minus B plus C is equal to negative 2. If I subtract those, 25A minus A gives you 24A, negative 5B minus negative B, so that's negative 5B plus 1B is negative 4B. C minus C is 0C. 7 minus negative 2 is 7 plus 2, or 9. So that gives me one equation and two unknowns. I can grab another 2 here, so why don't I take this bottom equation and the middle equation. So 9A plus 3B plus C is equal to 5, and A minus B plus C is equal to negative 2. And if we subtract, 9A minus A is 8A, 3B minus negative B, or 3B plus B, is 4B, C minus C is 0C, 5 minus negative 2 is 5 plus 2, or 7. So now I have these two equations. 24A minus 4B is equal to 9, and 8A plus 4B is equal to 7. Well, I see that I've got negative 4B and positive 4B, so I'm just going to put those right next to each other. 24A minus 4B is equal to 9. So I can just add those two equations together. 8A plus 24A gives us 32A. 4B minus 4 plus negative 4B gives me 0B. 7 plus 9 gives me 16. Divide both sides by 32, and I get A is equal to 1/2. So there's my start. I've got A is equal to 1/2. So I've got Y is equal to 1/2 x squared. Now let's solve for B. So I'm going to plug this into one of these equations here. Doesn't really matter which one. I'm going to use the top one just because 8 is smaller than 24. So 8 times 1/2 plus 4B is equal to 7. 8 times plus 1/2 is 4 plus 4B is equal to 7. Subtract 4 from both sides, and we get 4B is equal to 3. So B is equal to 3/4 plus 3/4 x. Now I have A, I have B. I just need to plug it into one of my original equations to get C. I think the easiest is A minus B plus C is equal to negative 2. So I've got 1/2 minus 3/4 plus C is equal to negative 2. So if I'm going to move these around, let's make that 2/4 minus 3/4 plus C is equal to negative, call that 8/4. So 2/4 minus 3/4 is negative 1/4, plus C is equal to negative 8/4. If I add 1/4 to both sides, C is equal to negative 7/4 minus 7/4. So now we have a parabolic equation that includes those original 3 points. And those original 3 points again were negative 5, 7, negative 1, negative 2, and 3, 5. So let's see if that works. I'm going to grab this one since it seems easiest. 1/2 times 1 is 1/2. 3/4 times 1 is, so 3/4 times -1 is -3/4, so I've got 1/2 minus 3/4, or 2/4 minus 3/4, minus 1 minus 7/4, so 2/4 minus 3/4 gives us 1/4, minus 1/4, minus 7/4 gives us minus 8/4, or -2. And we can do the same thing for those other ones. To plug it in, and you'll see that that is the parabolic equation that includes those 3 points. So that's pretty cool. Give me 3 points on a parabola, and I can turn it into a system of linear equations to find the equation for that parabola. Any 3 points on that parabola. So if you didn't think anything else in this was cool, that's pretty cool. And that finishes up 9.1 Systems of Linear Equations.